Good morning, afternoon, and evening to everyone, depending on where you are in the world. I'm Daniel Austin, and our talk today is called Getting Started with Web Performance. The first thing I want to tell you is, as Yasmina said, this is sort of a preview of my forthcoming book from O'Reilly, which is, surprisingly enough, also called Getting Started with Web Performance. And that book will be out, I'm told, very soon. And in fact, I believe that it's available for pre-order on Amazon today. The first thing I want to talk about as we go through the slides here is basically our goals for the class. The first thing I want to say is my apologies. It's impossible to present a really good, thorough understanding of web performance in 45 minutes. I'm going to give it a great shot, but I realize that this is just an appetizer or a preview. The goals that I have is I want to get you a basic understanding of how the web works from a performance point of view. I'm trying to target a lot of different people with this material: architects, developers, designers, engineers, anyone who's involved in building or creating the web. And of course, I want to give you the ability to identify problems and resolve them and make your pages go fast. The whole goal here is to make the web faster and smarter, and that's sort of been my mission through my career. We're going to talk a little bit about tools, talk a little bit about techniques. One of the goals that I have sort of off slide here is for you as an audience is I could really use some feedback. Tell me what material here is difficult or hard to understand so that I can turn around and use that to make my book better and help more people make the web even faster. So that being said, let's go ahead and get started. The first thing I want to talk about is just what is the scope of web performance? What are we talking about here? The web is a very large system. For our purposes, the web is anything that uses HTTP and URIs. We always talk about this from the end user's point of view. This is very important. The web basically consists of a client, some servers, and the network in between them. If we want to talk about web performance, we need to do this from the user's point of view rather than, say, from the server's point of view. So everything we talk about is in what I call the user narrative. Everything else that is on the web we're going to treat as a black box. This means that we're not going to talk about how to optimize your database, and this is the wrong place to help you optimize Oracle or the machinery that's behind your system. What we want to talk about today is how the HTTP protocol, the TCP protocol, the URI addressing scheme, and all the parts of the web that we know and love interact to make web pages fast or slow. But we're going to treat our servers as a black box and really focus on the web itself. The current state of the art. I like to tell people that this is really an art and a science. It's not yet engineering. What I mean by that is largely that we don't have a cut and dried methodology in many cases for accomplishing our goals with web performance. We're still learning about this. Standards and technologies are changing so rapidly that we're still in the art and science stage, not necessarily in the state of engineering. There's a lot of ad hoc methodologies going on out there. Very little of it seems to be based on some methodological reasoning. But things are getting better. One of the key things that's happened here is that the W3C, the World Wide Web Consortium, has started to become involved. They put out some standards around how browsers themselves can measure performance, and this helps give people a lot of insight into what's really happening. So there's hope. And as I've worked in this industry for many years, I continue to be optimistic about the future, and I feel like we really are making the web faster and smarter. There's not a lot of books on this topic out there. Here are some of the ones that I've found to be useful. Especially want to call out Steve Souter's book, High Performance Websites. I believe there's two of them. The second one might be called More High Performance Websites, something like that. Obviously, this is an O'Reilly book, and we want to give a big shout out to our host here. But these are also great books. One of the things that I had as a goal in writing my book was to help you understand why the rules in the High Performance Website book work, so that you can have a better understanding of that. when I'm asked what performance is, I get, a lot of funny looks when I answer because I always say the same thing. Performance is response time. We hear sometimes people talk about latency, and this is incorrect. There's a lot more to web performance than simple network latency. The network certainly plays a role in how fast the web goes, and it's a big role, but it's not everything. And I don't want to confuse the situation by talking about latency. I feel like if we talk about response time, which is what users experience, then we'll be a little more clear on this. So when we ask ourselves, what sort of problem are we trying to solve? Why should we spend money on performance? Why should we have people working on this, spending their effort and time on it? And the goals that we have for performance on our website basically come down to 2 or 3 things, right? We want to have a website that doesn't have performance problems. It has predictable performance, it's reliable, and on a day-to-day basis, you can reasonably hope to predict how well things are going to go. Obviously, we want our response times to be awesome. Now, people ask me, they'll say, I can't make my web pages go as fast as Google's. And so is it really worth it to do this? And I often tell people that yes, it is very, very worthwhile to do this. It's not a case of trying to make your website so much faster than somebody else's as trying to make sure that your website has no obvious performance problems, that you've identified the opportunities for optimization, and you have that world-class response time for your website, which isn't necessarily the same as what we might consider the right response time for Google or Facebook or Twitter. Another thing that we have to take into account is that performance costs money. Of course, we can make everything go fast if only we built, a data center in everyone's home. It's not going to work that way. What we need to do is find an efficient path toward making the web faster. And what that really comes down to is that this cost scales linearly with traffic. And of course, in the end, it's all about the user. This is the user narrative, and we want our users to be delighted. There's any number of slides out there and details from different companies about the impact on their business from performance. I've listed some of these here. There is a typo in the second item, by the way. My apologies. But when we look at these numbers, it's very interesting because A, they're all over the map. B, it's very difficult to see how this could really be measured and managed in a reasonable way. But if we take it with a grain of salt or consider it a first-order approximation, it's pretty easy to see that performance is really important to the user experience. Even 100 milliseconds in response time reducing revenue by some fraction is a big difference. And when you're talking about something like Amazon, reducing revenue by 100 milliseconds or 1% for that 100 milliseconds is a significant business issue. On the other hand, performance isn't everything. I'm an architect by profession, and one of the things that I spend a lot of my time doing is trying to make trade-offs among the various systemic qualities: performance, reliability, security. I work for a very large financial services company. Obviously, we're going to be very interested in security, and we often make a trade-off in favor of security over performance. And while that hurts my heart a little bit, I want things to go fast, I'm going to come down on the side of security. I would rather that your data was safe than get there more quickly. And this is sort of an illustration of some of the common trade-offs that we encounter in the performance world. And these things have to be thought through. Performance is not the only goal. And that sort of brings me to my first anti-pattern here. I know one of the initial advertisements for this talk talked about 7 principles of web performance or something like this, and I sort of changed the pattern on this and decided instead of presenting a sort of a 7 principles talk, I wanted to give you an overview of what's in my book and call out instead of principles some anti-patterns, things that I see people doing on the web that don't necessarily make things faster but can actually be harmful or have a negative effect. And this is sort of the first one, what I call keyhole optimization. A lot of times when we load a web page, there's many, many different steps and objects and activities that are taking place. And some of them will be more or less optimized than others. One thing I see people doing is deciding that they're going to optimize what's in their domain without thinking about the effect on the rest of the system. And this is a very large anti-pattern, a very significant one, because what it does is take resources away from other places in the end-to-end response time where it might be more needed. And we'll find out how to determine where to spend our time and resources as we go through the talk today. Some of the things that impact performance, as you can see, it's a little bit complicated. Geography is important. Where you are in the world is a prime determinant for the actual network latency, not the response time. The network location, this is, which ISP do you use, what's your effective connection type, your ability to get on and maintain a reliable connection. Obviously, bandwidth is a big issue. We buy our internet services usually on the basis of bandwidth, and we'll see whether that makes sense a little later in the talk. Transport type, are you on a mobile device? Are you on a Wi-Fi connection? Browser type matters. People ask me how much difference is there between browsers, and I've seen differences as much as 50% for the same page in two different browsers. The page composition, this is really where the high-performance website book spends its time, talking about how do you compose your pages so they'll be quick, and how to use the CDN, reduce the number of connections, and so forth. The page composition is not the only thing that matters, but it's a huge impact, and I wanted to call that out here. It just keeps getting more and more complicated, doesn't it? This diagram is basically showing all the various hardware pieces and the network path between your PC, maybe like the one you're sitting in front of now, and the network content or the web content that you're accessing with your browser. And you can see that it's fairly complicated. I'm not going to, in this particular talk, go into a lot of detail around it, but you can see that from the PC we go to the home router, we go out to our ISP's nearest point of presence. Pardon me. Our ISP provides a number of services, mainly that connection out onto the internet superhighway. And then we go off to the various web servers and co-location centers where the CDN nodes that have much of the static content in the web are located. The book, by the way, does go into a lot more detail about all of this. I wish I had more time. Everyone is always curious about this diagram and how things work, and I find it very useful, so I hope you do as well. One of the key themes in the book that I talk about is what I call the multi-step or multi-phase loading cycle that web pages go through. So I think we all understand that HTTP is a client-server protocol, basically based on the idea that there is a request made by a client, a response from one or more servers, and the data goes back and forth in this conversation. And that's what the slide here is sort of showing us, is we're able to see how the connection is set up. There's a handshake that goes on there. Then the request is made. The server thinks about it a little while. You'll see there's a gap there between those arrows. That's really the server duration, and we'll talk a little bit about that. And then, of course, the response comes back from the server, and you'll see that in this particular diagram, I had left no time to account for what the browser itself actually does. We often think of web performance as being the time taken to transport things over the network, or the time for the server to do its computation and prepare that content. There's also an element in the overall E2E end-to-end, that is, that's contributed by the client, how it's processing and executing JavaScript, loading files, rendering them, and so forth. I did not show that here, but it is a main theme of the book. So this is our basic cycle, and one thing I wanted to tell you about with that idea of the multi-step cycle is that in the normal course of events these days, when you're accessing a web page, we don't make a simple connection to a server and then wait on the response. What actually happens is we retrieve a base page object or a base HTML object or data structure. And that triggers a secondary set of lookups, usually out to a CDN to get images, CSS, JavaScript, various other things, largely static content, although not so in the case of JavaScript. And so there's this two-step process for loading a web page. First, we go and get the base page, then we make those secondary and transitive lookups for the more or less static content. And I want you to keep that process in mind as we go through our explanation here today. The MPPC model of web performance. MPPC is multiple parallel persistent connections, and this is a model for understanding web performance that I've been explaining to people and using for about 10 years. And there's a lot of people in the industry who tease me about this just because I've been at it so long and saying the same thing. But I think being really consistent about this has been very helpful in getting people to understand the model. But just looking at it, the basic idea behind the MPPC model is that we divide the time taken to make an HTTP request and response into several time segments functionally based on what the server and the client are doing. And then we look at the individual time spent doing those tasks. And if we need to, we can break those tasks down even further. And this helps us identify the delays. So the model is basically divided up into 4 time segments. And they're very simply called T1, T2, T3, and T4. T1 is the connection time. This is the time that it takes to actually make a connection to the server that's going to respond to your requests. And believe it or not, just setting up a connection takes a considerable amount of time and is actually a rather complicated process. When I show people a sequence diagram, and this is in the book, of what actually happens when they make a connection to a website, they're often amazed at the complexity of it. T1, the connection time is a significant part of the overall end-to-end, and we'll talk a lot more about that. The T1, by the way, is basically the sum of the time taken to perform the DNS lookup, to do the TCP connection, to establish the secure SSL connection, if any, and then once those steps are made, we go on to the second step of server duration. So those are basically that's basically the breakdown for T1, those initial steps for establishing the connection. The server duration is pretty straightforward. I think everyone can understand that once the server has received that HTTP request, it has to think about it a little bit and perhaps make some behind-the-scenes calls to databases or other systems in order to present that data back to the user. All of that obviously takes a certain amount of time, and that T2 time accounts for the server duration. The T3 transport time is the time basically taken, pardon me, the time taken for the data to be transported over the network. This is where our network latency actually comes into play and has an effect on the user experience, is that T3 transport time. And obviously that involves some understanding of TCP/IP and the underlying network. The rendering time, this is what I was talking about, the time taken by the browser to perform whatever actions it needs to take in order to get that web page ready for you to interact with it. So our model is based on breaking the end-to-end response time, and this is for a single object in this simplified slide here, into these 4 time segments and analyzing each of those. One of the first things that's pretty obvious about this is that if you break the data down, it'll be very easy to see where the delays on your website are. So here on the slide is some data for a lot of different websites. In this particular case, these were taken from the Media Metrics top 100 websites. And what I'm looking at here in this particular case is SSL performance. All of these connections are SSL. And you can see here in the top series distribution graph there that I've labeled these things T1, T2, T3. In this particular set of tests, I did not include the T4 data because I wanted to look at the performance at the network level. One of the first things you see here, of course, is that T1 times are overwhelming for these websites that use SSL. And the book goes into great detail talking about the performance of SSL and how to make that better for users. But I don't want to go into detail about that right now. What I want you to get from the diagram here is that by using our model, our previous model, we can break these things down and look at where the time is spent and how to make that faster. This immediately gives us some ideas about where our problems might lie, if there are any, and what our opportunities are for optimization. The second graph down below that one there is the actual breakdown of the individual steps. It's just a more detailed breakdown of the data in the upper graph. And you can see that I've labeled the DNS time, the TCP connect time, the SSL time, the first byte time. This is the time that it takes for the server to return the first byte of the response, and then the time for the last byte of the response to be sent, the content time. And in this particular graph, you can easily see that the SSL times are overwhelming all the rest of the response times for these websites. But the key thing here is that by analyzing the data this way, we can immediately see where the problems are. Now we can go and start analyzing solutions and picking the right one. One thing I wanted to make a big point about is bandwidth and latency, and this is especially important in some of the discussions. I don't know if anyone has been following about net neutrality. And so let's see if we can find a way to understand that a little bit. So bandwidth and latency, fairly straightforward. Your intuition about your garden hose is going to, be suitable for this. The basic idea is if there is a big pipe, large bandwidth between you and the server, then the image itself will come down more quickly. It occupies less space in that pipe. Small pipe, big response time. Big pipe, small response time. Very straightforward, very much the same as if you think about hoses of different sizes and water flowing through them. The folks at Google have made a point of talking about the impact of bandwidth and latency, and I stole this graph from them. Thanks, guys. The point that they make here in this graph is a very important one, and it's about bandwidth and latency. So bandwidth is the greatest volume of data that can be sent between yourself and the server. It measures the volume of some data. The latency is the actual time it might take for the data to go from A to B, from the server to the client. There are two different aspects of the network, and they have different performance impacts. And this is really, really important for understanding performance. In that top graph, we talk about what happens when bandwidth increases. So you can see our response times here at 1 megabit per second, 2 megabits, up to 10 megabits. And you can see immediately that once you get to about the 5 megabit limit, that we see startling diminishing returns for increasing bandwidth. And it doesn't look like the response times at 6 megabits are vastly greater than they are at 10 megabits. And if we extended this graph out to 50 megabits, we would see that that our response time improvements are minimal. Once you get past the 5 megabit limit with TCP, there's few returns for increasing bandwidth. Latency, on the other hand, is very different. We can see right away that looking at that lower graph that there's a linear relationship between latency and response time. And the more we reduce the latency, the better the response time gets up until the speed of light limits or the limits of processing on our machine. So if we're going to spend money and time improving response times, we'll only get so much bang for our buck spent improving bandwidth. But every dollar we spend in reducing latency is a dollar well spent in improving the user experience. So having said that, and these facts are pretty well known in the industry, you might want to think about what net neutrality means and what an ISP might offer a company like Netflix when they say they're going to offer them a fast track on the internet. Are they going to offer them more bandwidth? That would be good, up to about 5 megabits. After that, it's not going to help anything, and any money spent would be pretty much wasted. Are they going to decrease latency? If so, I think the rest of the world would really like to know how they're going to do that. Decreasing latency is very difficult and often very, very expensive. The costs are prohibitive. So as you think about net neutrality and you read these things in the internet, you might think about bandwidth and latency and wonder whether you're actually getting a good deal or hearing anything from people who understand what's going on. And that brings me to my next anti-pattern, which is one that really, really makes me crazy. I call it, that's outside my control. And I hear this from people all the time. People will say, my DNS times are poor, but there's nothing I can do about DNS, so users will just have to suffer. And it's my contention that it's never the case, that there's nothing you can do about a performance problem. Even if you can't address the DNS problem, you can compensate for that somewhere else in the end-to-end response time. You can find a way to mow around that rock in your yard. You might not be able to move it, but there's always something you can do. And despairing and saying, oh, there's nothing I can do about that, it's outside my control, is an anti-pattern that you really, really want to avoid. Think outside the box. What else could you do? So let's talk a little bit about tools. So the web performance space is chock full of tools. Unfortunately, most of them are not all that great. The part of that is simply the fact that it's a difficult problem. It's not so easy to get an idea of what's happening with users without actually being that user or being in some internet context that resembles that user's context. And so web performance testing is very difficult. And so we have lots and lots of tools, and they often tell us many different things. One of the themes that I have when I'm teaching people about performance is to learn how to use the tools, test things for yourself. That's so important. And learn to use a lot of different tools, understand what they're going to tell you so that you can not only use the right tool, but that you can get multiple different views from different sources of data and get a full 360 view on what's happening. Some of the commercial services that are available out there, there's the CompuWare Gomez product. Keynote is a competitor to them. AlertSite and Thousand Eyes are newer sites in that same newer products in that same space. All of these work in a very similar way. They involve a lot of wholesale testing. They're essentially statistical measurements. You take thousands of measurements and you do some descriptive statistics to understand what's actually happening. You are able to get some good measurements under different conditions. You can test, using different browsers and different devices. And this is really the best way for understanding what's happening, for instance, in the international market. If you want to understand what your web performance is like in India, and you're not able to actually be in India and test that. Also, a best way to understand how the actual network performance is performing as opposed to broken links or slow JavaScript. The commercial services will help you a lot with understanding the network performance. There's a lot of desktop tools available as well, and some free online tools that are more or less desktop-based because they produce measurements one at a time. And these are good for spot measurements. It's retail testing. You're testing one page or one app or one page sequence at a time. And this is usually diagnostic testing. If you want to identify that JavaScript that's running slow, if you want to identify a problem, these tools are really good for those situations. Some of the tools that we're talking about here, there's YSlow, and disclaimer, I was a member of the exceptional performance team at Yahoo that built YSlow for many years. There's a product from Microsoft called Virtual Round Trip Analyzer. This is my personal favorite tool for spot measurements. There's a commercial tool called HTTP Watch, provides a browser plug-in. You can find some others, but honestly, for retail testing, one of the best approaches is simply to use the browser-based developer tools. You can usually do that just by hitting F12 in your browser, and it will bring up a display showing you something about the overall performance, usually a waterfall diagram. And so these are our basic classes of tools, and I want you to get that distinction between wholesale, real-world testing, and retail testing. Don't come to your boss and say, well, this page loaded in 5 seconds on my desktop, because your desktop is not important for the user's experience. It's really not, especially if you're sitting in a corporate headquarters in Silicon Valley. The commercial testing services, let's talk a little bit about this. They are, in the first case, actually very similar. This is a synthetic test setup. It's synthetic in the sense that it is not monitoring the real activities of users, but performing a canned set of tests in some sequence that we've set up, a little science experiment that we've created, rather than observing what users actually do and taking our data from there. That synthetic test setup is a good balance between the sort of clean room lab test setups and the ability to measure things on users' machines, which we really don't have in many cases. Synthetic testing offers us a good balance between those competing concerns. These companies usually have test nodes in large data centers and Amazon Web Services in their own data centers, and in some cases they're actually out there running software on users' machines. And to some extent, this is the gold standard for end user data, is that what we call last mile data. You get a lot of statistical data about response times from this. If you look here, you can see on the graph that I'm actually plotting the SSL response time, I believe, for the PayPal homepage. You can see that I plotted the standard deviation on top of the response time. What I'm looking for there is to understand the variability of the response times. And that's a really important point when you're analyzing this. One of the things to look for is variability, not just the actual single number for the response time at any given time. The performance testing locations that you can use with these commercial services basically fall into 3 groups. You can set up these test nodes in your own data centers. This is not necessarily very useful for performance testing, but it's probably useful for monitoring the reliability and uptime for your machines. There's the backbone distance segment or location segment, and this is largely a set of large data centers. People like Sprint and AT&T run these large data centers, and by putting the performance testing nodes in those locations, we can get a fair idea of what things look like on the network. But we need to remember that no user ever sits in a data center, and that the experience and response times we see for backbone data are completely unrealistic, have nothing whatsoever to do with the user experience. It's still useful for diagnostic purposes, does not provide a lot of useful information with respect to user experience. That data has to come to us from the last mile time segment, which is where end users, poor souls with mice in their hands like you and myself, or maybe a mobile phone in our hands, live out in that last mile segment. And the last mile really refers to that distance between yourself and the ISP. The commercial tools can give you measurements from each of these different locations, which is also very important, because by looking, for instance, at the difference between backbone and last mile data, you can understand the contribution to the response time that comes uniquely from that last mile time segment. You might be surprised at just how much of the overall end-to-end comes from the last mile. On the other hand, you might ask yourself, why do we still have last mile problems if we're all hooked up to the cable network? I mean, there's a complete cable connection end-to-end between my house and Google. Why is it so slow? Desktop tools. Everyone should have some of these. it's very useful to be able to whip these out when you need them without thinking too hard about it. Everyone has their own favorite set of desktop tools that they like to use. I'm going to give you some suggestions. You don't have to use any of these, but these are all good tools. Obviously, the browser developer tools obtained from hitting F12 is a good source. YFlow, developed by Yahoo and the Exceptional Performance team, implements the famous YSlow rules. These are heuristics developed by Yahoo to make pages faster. They're outlined in that book that I was telling you about earlier and discussed in detail in my book as well. Microsoft Fiddler, Virtual Round Trip Analyzer is available, HTTP Watch. There's also the common Unix command line tools, ping, NSLookup, dig, tracerap, netstat. All of these are essentially network tools that will give you some idea of what's actually happening at the network level. None of those Unix command line tools will give you very much data about HTTP connections, with one exception, and it's a tool that I didn't actually mention on the slide here, and I should, which is the curl tool, which actually does make an HTTP request and gives you some insight into the HTTP level response times as opposed to what's happening at the TCP level or the DNS level on the network. Tools for mobile testing. I haven't really been able to talk much about mobile in this presentation simply because we have so little time, but some of the tools that we have available for mobile testing beyond the commercial tools, you can always go to speedtest.net from your phone and see what your bandwidth is, get an idea of your ping times and some idea of the variability between these things. I want to encourage you to do that. One of the things that I do, and people think I'm crazy, but one of the things that I do is I'll just sit and randomly measure the performance wherever I happen to be sitting in the airport or the restaurant or wherever, just so that I can understand and get some experience in that data. There's a tool called iCurl for iPhone users that does basically what the curl tool for the Unix command line does. I don't know if there's an Android version of that, but I hope so. There's a version of HTTP Watch Basic for the iPhone as well. It costs $99, very expensive app, but there's a basic version that's free. In some sense, this is the gold standard for performance measurement on mobile devices simply because you can get a great waterfall and you can compare it to the waterfall that you see from using it on the desktop. It's very instructive to see the difference in loading between the mobile device and the desktop device. So I'm kind of hurrying through the last part here. The one further tool that I want to bring to your attention is called webpagetest.org. This is an online website. It basically mimics a lot of the features of the large commercial tools, such as Gomez and Keynote, but it's available to you for free. Obviously, you can't do statistical levels of data gathering with it. You're doing essentially spot measurements again, but it does give you the ability to choose browsers. It does give you the ability to choose locations and provide some really useful data. The waterfall diagram here on the slide, and I need to move that over a little bit, is basically showing yahoo.com's waterfall taken from webpagetest.org, and you can see here the breakdown for the MPPC model. Each of the colored time segments in each one of these bars corresponds to the DNS lookup times, the TCP, the connection time, server duration, and so forth. So the webpagetest.org tool is very useful for you. I encourage you to do that. In a lot of cases, I try to do a hands-on exercises in my talk, but I'm running a little short on time. I can't do that today. I want to encourage you to just go to this website and try this, whether you're able to do that during the talk today or not. Very interesting. One of the key skills to analyze performance is reading waterfall diagrams. Make sure and learn how to read waterfall diagrams. Very key competency. Our next anti-pattern, design time failure. One of the things that people often fail to understand is that you can't fix this stuff later. You really can't. Performance is a design time activity. You have to bake it in up front. You have to make performance a first-class citizen in your own mind when you're designing this stuff. releasing a product without testing its performance or being concerned with performance is such a bad move, I don't even know where to begin. But I want to bring this one up to you and just stress it again. Bake it in up front. Make sure that you've thought about the performance. If you design it, get it out into production, you find you have horrible performance problems, you will not forgive yourself. Your users, more importantly, will never forgive you. I want to give you just some ideas. We wind down toward the end of the talk here of what we face when we're looking at mobile performance. Mobile is super important to the web right now. Everybody is surfing on their phone, on their tablet. But the performance on these devices is sad. There's no other description that I have for it other than sad. If you look at a basic cable line, you look at your 4G and 3G networks as shown on the diagram here. And I admit this is a couple years old. Things have gotten a little bit better, but not so much. So we're still facing a real uphill battle in the mobile space. One of the things that I want to encourage you to do is to set your expectations accordingly. What is realistic on mobile is not necessarily the same as what's realistic on your desktop. And you may have to abridge your content, modify your content, do whatever it takes to make that mobile experience better simply because you're facing this response time deficit. Some best practices for mobile devices. And these, when I was practicing last night, I realized that this is good advice for everyone. There's a couple things here that apply specifically to mobile, but this isn't best practices just for mobile. This is best practices for everyone with some caveats for mobile. So let's look at this. The first thing, tread lightly on the JavaScript. I don't think anybody will have any difficulty understanding that if you're going to run a JavaScript interpreter on your phone, it takes some time and energy. Don't touch the DOM. This is a great rule for performance in general. DOM manipulations are extremely, extremely expensive. I've seen people create elements out of thin air, which you can certainly do with JavaScript, and they're always surprised at how long it takes to actually create an element or modify the DOM. Avoid that. CDNs in the mobile case, less effective due to network challenges. If you think about our model, it explains that very easily. The CDNs are less effective simply because more time is spent in T1 getting the connection made than is actually spent downloading the data. Our model immediately leads us to an understanding of why these rules are true. Same thing is true for the time to first byte isn't a good measure for the server duration simply because that first byte may have meandered its way to you through a very long path. I do recommend using web workers for preloading simply because this will help your mobile users try to anticipate the content that you're going to send them next. One of the key things about mobile that I just can't stress enough is testing with different transport types. People are often amazed that 3G and 4G are not really the same. They're not a linear 4G is not a linear improvement over 3G by no means. And in some cases, 3G actually performs better, believe it or not. Try the different transport types. Test your battery consumption. If you try to load Etsy's web page, and I don't mean to pick on Etsy, I love Etsy, but if you try to load their basic web page on your mobile device, you will soon find your battery in desperate need of a charge. Think about that before you load thousands of images. The other thing that I want to just give you some insight on mobile is that you can anticipate 1 to 2 seconds additional response time maybe on your mobile device, maybe 1,000 milliseconds for 4G and 2,000 for 3G. Those are approximate figures, but it's very consistent globally in what we see in terms of the initial delay associated with mobile devices. And our last anti-pattern here is spending your time in the wrong place. The mobile experience is very different from your desktop performance. You have to go through and use the MPPC model, look at those two cases for mobile and for desktop, and you'll find that the distribution of the response times is very different for these two user experiences. A lot of time is spent on the network and on connections for mobile devices in proportion to the time spent for the networking aspects on the desktop. And this is a key thing to take into account when you're building mobile devices. I stole this diagram from my friend Nick Zakis, who has a great book on JavaScript performance out there, and kindly allowed me to steal his slide or his diagram here. What the purpose of the diagram is simply to talk a little bit about division of labor and where the actual activities should occur. Obviously, we want the server to do its job. We don't want to try, for instance, to do things in HTML that should be done in CSS. Do things in JavaScript on the client that can be easily done on the server. Part of good web design is understanding how to use these tools in the right combinations to achieve the best response time. I don't think any performance talk would be complete without mentioning the why-slow rules. So here they are. I'm hoping that you've seen these before. I'm not going to go in detail through each one of them, because I want you to come back and look at these slides and study them. And I want you to print this slide out and post it on the cabinet up above your desk. At Google at one point in time, they printed out the why-slow rules and printed them on the back of the doors in the bathroom stalls. I was very tickled by that. But it made a point. These are the things you want to keep in mind every day for performance. Please study these. Think about the why-slow rules. So as we wind down through the talk here, I just want to offer some advice and best practices here. The first thing I want to say is that every tool has its place in the universe. My own background is in cosmology and astrophysics, and as a scientist, I spent a lot of time looking at data from multiple different telescopes and tools, trying to figure out what was going on. I want to encourage you to do that same thing. Don't get addicted to any particular tool or technology. Every tool is a good tool, has its place. This slide actually was stolen directly from Kenny Toyer, who worked with us at Yahoo on the exceptional performance team. And I can't improve on this slide, so I stole it and I repeat it in my talks. But thanks to Kenny for this. Make your performance a priority. I already talked about that. Test it for yourself. I can't stress that enough. Learn the tools, balance performance, track your results over time. This is something I see that people don't do that they should. They have no idea what their performance was like 6 months ago or a year ago and had no real basis for determining whether they've improved in the long term. And it's not necessarily the case, of course. The response times will generally go down. You may add things to the pages. That's okay if users want that, but you should track your results over time so you can understand the impact and the progress of your site. Setting targets, obviously, you can't solve problems or improve things without having some goal. And the last thing I want to encourage for you is to ask questions. Check it for yourself. Don't believe anything that I say. Check it for yourself. Don't believe anything that anyone says. Test it for yourself. Believe your own data. So one question that I often get is, how fast is my website in India? Or, can you make this website a lot faster? How fast can you make this website? How fast is our website today? I hear this a lot from bosses. One of the main answer I like to give people is, 42. I don't know. Nobody really knows what the performance is in India today. It's a continental plate. We can't really talk about that in any rational sense. And when your boss asks you a performance question that has no meaningful answer, the correct response is 42. And then once your boss looks at you funny, you can explain why that's the case. This stuff is complicated. There's no simple answer or one number of truth. If you're curious about who to blame for all of this web stuff, well, this guy here, Tim Berners-Lee, is the one responsible. I encourage you to send him an email and give him a hard time about it. This quote here is from the original project proposal from the web. And we all need to thank Tim for the work that he's done. The last thing that I want to say here is that in the end, performance is ultimately about respect. Respect for your users, respect for the people you work for, respect for the project that we call the web. So that's basically all I have to say. My Twitter and email address are here on the slide. Thanks, everyone.